all of the participants. So, respected principal, vice principal, deans, HODs, esteemed resource person, dear faculty member and participants, a very good evening to one and all. It gives the immense pleasure to welcome you all. Once again, sir. So it gives me immense pleasure and pride to extend a warm and cordial welcome to our distinguished chief guest, Dr. Perumal Raja, for today Faculty Development Program chief guest. Dr. Perumal Raja is a highly accomplished academician, researcher, administrator with more than 15 years of rich experience spanning teaching, research, administration, and industry. He holds He holds a PhD in electrical and computer engineering from Carleton University, Canada, and has an impressive academic journey that blends global experience with deep-rooted contribution to Indian higher education. Our chief guest served in several prestigious leadership roles, including teaching, including vice principal, dean, planning and development, and professor, head of various departments. He has played a pivotal role in MBA and NAC accreditation, NIRF, and innovation ranking, faculty recruitment, and infrastructure development, and implementation of sustainable technical education practice. Dr. Perumal Raja is also an eminent researcher in wireless network, AI, generative AI, quantum computing, IoT, and network security with 400 plus Google Scholars citation, publication in reputed IEEE transaction and international journals, several patents, book chapter, and funded research projects supported by AICTE and DST. So the funded research projects are AICTE in sanctioned amount is shown in the slide. And what truly sets him apart in his unique ability to seamlessly integrate academic excellence, research innovation, administrative leadership, and industry relevance, making him an ideal mentor and guide for faculty members in today's rapidly evolving academic ecosystem. Sir, your presence today adds immense value of faculty development program. We are confident that your site's experiences and guidance will inspire and empower all the participants. On behalf of the management, organization committee, and all the participants, I once again extend a heartfelt welcome to our Dr. Perumal Raja and thank you for graciously accepting our invitation. Thank you, and we look forward to enriching and insightful session. Thank you, sir. Welcome, sir.
Thank you so much, ma'am, for giving the wonderful introduction.
Thank you, sir.
I would like to thank the Almighty for making this today's event. Next, I would like to thank the management and then HOD CSC and traveling along with me and as a coordinator of you. And thank all the participants for participating in today's event. Very like a bi-directional way of communication. So let us go into our today's session. It's LLM fine-tuning and adaptation. I'll share my screen. Yeah. Would you be able to like see my screen?
Yes, sir. Yes, sir.
Yes, sir.
Yeah. So in today's session, what we are going to discuss is fine tuning and adaptation of LLM. So why this topic is matters today? Um, Sometime before, it's AI is a buzzword. Maybe 5 years or 10 years before, AI is a buzzword. So everywhere, wherever we go, for any student want to come for research, they will, are interested in doing AI, and this is the buzzword it was there. Nowadays, it's from the last 5 years itself, it was changed into generative AI and especially on LLM. So LLM is a why LLM? Because LLM is a right like now power search engines, chatbots, coding assistant, and teaching tools and enterprise and automation. So almost all the industries in all the sectors, right, they are using LLMs because the whatever we are looking for any as a customer support or anything, even for an employee, right? That LLMs gives the reduces the work, and it fine tunes and as well as gives the whatever you want, it gives the exact the response. Companies need LLM that behave consistently and follow the domain rules. Follow the domain rules means because each domain, wherever you go, either the healthcare sector industry or educational sector or anything, right, that is important. So they should behave very consistently. They should avoid the hallucination. Hallucination means, right, it looks like a correct answer, but it is not actually the correct answer. So that hallucination has to be avoided. So that's what we are more like looking for the quality on quality or the efficiency of the LLM. So, and moreover, like since the company is more interested, faculty and students are they understood that when we work on LLM and do research on that, then only we will be able to sellable. So, how to customize this model efficiently, not just use them. Here, the fine-tuning and adaptation enables the organization to build the domain-specific intelligence with respect to retraining from the scratch. So knowing this pipeline is critical for careers in AL, machine learning engineering, NLP, and applied research. So what like we are going to see in today's session. So how LLM evolved from the basic transformers to multi-billion parameter models? Why prompting and retrieval were not enough for many real-world use cases? And how fine-tuning emerged as a stronger technique for deep domain expertise? And about we are going to see something how fine-tuning and adaptation for some real-time use cases, and then how modern methods like low range adaptation and quantized low range adaptation change the landscape of today's requirement. So here, how fine tuning works in real time, we need to show it in a demo, because right, whatever we are seeing in today's chatbots or whatever, when we use LLM and finally when we are getting answer only, we are seeing the answer in the front end. So user interface is there. But we supposed to know in back end like how it works and all right. Then I just connected. So it would be easy to understand and realize. So that's what I asked my student Santosh to give a demo on that. So that's what going to end with that. So first, before we get into that LLM, we need to first just I want to say a few words about the recap of the technology. As I said earlier, 5 10 years before, the classical machine learning and deep learning models are right are very predominant, and they designed for the sequential processing and struggling with huge data sets. Because right, if you give a, limited data set, then the efficiency, especially right, when you see the hallucination and all, it would be much more. For example, even I could remember the days when the students come up with results. Sir, I was able to, I used to verify the scores, F1 scores, and whatever everything and everything, accuracy, precision, and everything. Like when I look into that, almost it's perfect. It's like 100. Now
Deepa ma'am,
99.
Deepa ma'am, ஒரு நிமிஷம். Sir, once again, sir.
Yeah.
Deepa ma'am, sir, please continue, sir.
Yeah.
Uh,
So I would be able to like see that the students come up with very good results. How it is possible? AI is artificial intelligence is not definitely it is not going to be perfect as like a human. Then how it is possible? Because that's a hallucination. So when we give a huge amount of data set, then only your model get trained and then only it will be able to like give a good results. Because for example, when you are training the model with the limited data set, then if you give the testing data with a similar type of test data, then it will give a perfect result. So there is no point in developing that model. So that's what when we give a huge data set, then only it will be able to like train quite a lot. Then because I could remember the one of the meeting with Aravind Aikar, and Google is the for their especially retinopathy, right? Like for that identification of retinopathy, they are the implementation partner. They have developed with millions of data. Then only they are able to like predict the retinopathy, diabetic retinopathy. So at the time I was able to like interact with people, right? At the time only I come to know the huge amount of data set is highly required to getting like a precise value. So that's what the classical models struggle a lot. So that's what the transformers get into picture. Transformers use a self-attention mechanisms and process the entire data sequence in parallel. So they will collect all the like a related data set as a embedding vector, and that allowing them to capture the global dependencies and scale to the enormous data sets. So what is the key difference at a glance between the classical model and transformers? Because before LLM, the transformer is one like evolution, the beginning stage. So the key difference between the classical model and transformers, right? The data processing is classical model huge and transformers are limited. And with the respect to the contextual understanding, the classical models focus on local features and transformers and self-attention allows them to like weigh the importance of any parts of data regardless of distance. And training and data requirements, transformers are data hungry and requires large data sets, but whereas the classical models can often perform better for a smaller data sets. So computational resources, right? But transformers requires it handles the huge amount of data set. It requires computational power is high. They requires GPUs and memory. And the classical models are generally lighter and easier to deploy in resource constrained environment. So this is the evolution of LLM. So in 2017, the transformer was introduced by the researcher Vaswani, and it eliminating the recurrence. And 2018 to 20, the rise of the transformers model, BERT and generative pre-trained transformer 2 and Robert and early large-scale language understanding. So they started understanding the languages. But if you see the previous old chat GPTs and all right, it's the prediction was it's very poor. So you would be able to like see quite a lot of hallucination. So in 2023, 20 to 23, the GPT-3, T5, ALM, Llama scaling laws discovered and leading to the massive model sizes. And 23 to 24, the efficient techniques like LoRa, low range adaptation and portraiture low range adaptations are enabled, and they reduces the 70 billion models to 7 billion models and cheaply. So in 2025 plus, the agentic LLM and specialized domain models push need for the deep customization. So there is a brief history of the LLM. So this is the generative AI project life cycle. So first we need to define the use case, what actually you are looking for, and then you have to go with choose an existing model or pre-train your model, because you need to without pre-training you cannot it will go like every time you have to go with like a huge data set for getting the answer. So once you pre-train the model, then go with the adapt and align the model. So that's what the prompt engineering, fine tuning, and align with the human feedback. So evaluate. And finally, once the application was evolved, then developed, then integrate with your exact application, optimize and deploy the model for inference and augment model and build the LLM powered application. So here, when you see that this is the prompt engineering, that fine tuning and align with the human feedback, these and all, the adapt and align model, right? I would say this is the heart of the model. I think in first day of FDP, we would be able to like see that what is LLM and the basis of the LLM and all those things. And yesterday's session was really good, and with complete the pipeline and architectures and everything, we will be able to like see that. So once we saw the architectures, then we need to see that exactly how we are developing the model and fine tuning and adapting that model. So that's what we are going to see. So that's what I would say. This is the project. So here, once we have developed the LLM, that LLM customization, see, because the purpose of coming to the LLM is to avoid hallucination and all those drawbacks that exist with the older, the classical model. So the various LLM customization techniques that are researched by the various researchers are right, like prompt engineering, RAG, retrieval augment generation, and fine tuning, decoding strategy, agent, and RLHF. So reinforcement learning with the human feedback, RLHF. So these are all the LLM customization strategies. So the purpose of this introducing this customization is right to improve the efficiency of the performance metrics, right? We need to like take care of the performance metrics. So then only your model will be able to work well for your requirement. So this is the comparison of some of the LLM customization strategies, prompt engineering, RAG, fine tuning, and that and all. What are the customization what we have seen? So what it is exactly, what the prompt engineering. So it's crafting the effective inputs to guide a basic LLM existing knowledge. So simply, right, very even when you ask something with Google, even normal Google search engine, if you give a correct prompt means right that your search quotation right that your word, if you give in an exact way, you'll be able to get a like appropriate answer. Suppose if you search word is not appropriate, and then you cannot get the exact what you are looking for. So that's the thing. So similarly here, right, the prompt. So when your model is up to certain limitations, then if you ask a prompt, first you need to train the LLM, and then so once you train the LLM, so then only with some various prompt, after asking so many inputs, giving so many inputs, the LLM will get trained. Once it gets trained, then only it will be able to like give a at least appropriate answer. So that's what the fine tuning of asking that prompts, right? That's what the prompt engineering. So where it is best for, it's a quick experimentation and formatting simple rules, creative writing, and the pros of using the prompt engineering is very low cost, immediate updates, and high flexibility. And what is the drawback of using the prompt engineering, right? I cannot add a new knowledge limited by the base model because that's a base model only. So then we moved into the RAG, so retrieval relevant documents from the external database and provides them to LLM as a context to the answer question. So whatever you are asking, right? So that RAG, right, that will give a vectors, and then based on that vector embedding, and then from that vector embedding, it will look into that what you are exactly looking for, and then give me a sec. Sorry for the interruption. Sorry. Meeting sorry. So here, right, RAG will where the RAG will best for. So it's a factual accuracy, up to date info, private data, and reducing the hallucination. So the pros of using a RAG, right, it's high accuracy and dynamic knowledge updates, transparent, but the cons is high complexity because of the RAG architectures, and then cost than PE and prompt engineering needs a data pipeline. And then we moved into the fine tuning. Here, fine tuning training the pre-trained LLM. So already as I said, every time we cannot train the LLM. So we need to like take the pre-trained LLM on a specific data set. Then we need to inject the new skills or the domain specific knowledges. If we inject it, then it will be able to like give a appropriate answer. So then it's best for deep domain expertise and the specific outputs styles. So the pros is deep customization and task-specific performance. So here the cons are drawbacks of the fine-tuning, right? High compute because you have to after pre-training, right? You have to play with all the parameters, compute complex, and requires curated data and knowledge updates need retraining. And the next one is reinforcement learning from human feedback and then LLM agents. So here, right, the reinforcement uses the human preferences of the data. So whatever you are giving input, then it will based on the human feedback, it will train, and then finally it will react. Train a reward model, and then uses the reinforcement learning to fine tune the LLM to maximize the rewards. And best for aligning the model and based on the behavioral. So normally how the human will react when you do the right thing, then they will appreciate it. When you are not doing the right thing, then they will give a sometimes suggestions, sometimes you are not accepting. So based on that, the human behavioral, it will feedback, it will do that fine tuning, right? So then it's like this is the advantage. Highly generalized aligns with the nuanced preferences, and but the cons is very high resource demand and especially need a human involvement. And what is the LLM agent here? So LLMs that plan use tools like search, code, execution, maintain memory, and execute multi-stage workflows for complex tasks. So it's best for autonomous tasks completion of because agents it will work without any human intervention because on for replacing the human only you are implementing the agents. So autonomous task completion. So first already as I said, this is what the prompt engineering. So first you are sending the your prompt, and then it will regular response. So then you are improving the enhanced prompt, and then it will learn based on whatever you are fine tuning and sending the prompt. So this is what the prompt engineering. So normally what you need is already your base LLM is that's more than sufficient for prompt engineering. But you need to learn how exactly you need to like give a prompt. So maybe the faculty members who are in the serum, they are able to they are trained to like give a very good prompt. So we have given quite a lot of instruction for them to how to like give a prompt for getting a right appropriate answer. So that's what the prompt engineering. And why not just prompt is not cannot be used for real time, especially in various industries use cases, because prompting gives temporary instructions, but it cannot enforce a consistent long term behavior. So prompt right it will fail is it requires domain specific reasoning because without any even when you are asking for your subject or something, right? When you give quite a lot of input about the subject and all the course outcomes and everything, when you give, then only it will be able to train. Without giving so much data and without giving much more learning by various prompt, it won't give a right appropriate answer. So that's what the prompt fails when the task requires a domain specific reasoning. So prompting increases the input length, latency, and making the enterprise usage expensive. So prompt cannot override the deep model biases or hallucination and tendencies. Eventually, organizations realized we need the model to learn, not just react. So next we moved on to the RAG, so retrieval augmented generation. So if you see that, so first here, right, whatever when you compare with the prompt, so here the prompt that can be given. So when you are given, right, the company specific data, especially the embeddings, right, that stored as a vector database, and when you are asking, that will refer the search the vector database with the prompt, and then finally retrieve the relevant information related to the prompt. That prompt will be augment and original prompt with retrieved info, whatever with the vector database, that will be sent to the base like LLM and generate and finally give the answer. So that's the implementation of RAG. But still, there is a limitations of RAG. So RAG, right, it retrieves the documents, but does not change the model's reasoning engine. So if the model misinterprets the retrieved context, then RAG cannot fix the logic. So RAG will fail when the task requires the procedural reasoning, format rules, or strict safety alignment. So RAG works for adding the knowledge, but not for enforcing behavior. So this gap created the need for the model level customization is highly required. So that's what now we move into the fine tuning. So what is fine tuning here? So here fine tuning, right, the prompt for organization use case, and it will first we need to take the fine tuned LLM. So base LLM we have. So from the base LLM, we are giving the task specific training data set is there. So this base LLM and task specific training data set only your fine-tuned LLM is there. So LLM, right, with the base LLM, whatever the specific domain specific data or whatever, if it is educational, then educational specific data. And especially again, so come to subject, come to your department, again subject, again specific, right, those whatever task specific training data set will be learned, and as well as from the basic and finally you are getting the fine-tuned LLM. So fine-tuning involves adjusting the model parameters for the task-specific data set. So this process can be applied to the pre-trained model, effectively training it to the handle the task like sentiment analysis, text generation, or document similarity detection, etc. The benefits of using fine-tuning methods, right? Enabling the model truly learn from the data, not just access it, and guiding the model to produce more consistent results. As I said, not just the base LLM. So you are giving a specific data set or specific query and answers. That kind of data are also available in the specific trained data set. From that, it will take that learns and then finally it will give the answer. So reducing the instances of hallucination. So since it's giving the appropriate correct answer, your hallucination is eliminated. So customizing the model, we are doing it, right, for it. So need for adaptation is emerged. So here in the fine tuning and adaptation, sometimes some kind of like a small ambiguity may come into the picture. So, full fine tuning means you are changing completely all the parameters, but adaptation, right? Adapt with that environment, whatever the company specific data set. But here, another thing is adaptation, especially not placed with all the parameters of the whatever the data sets. So the LLM size is right because it's exploded. When we are using the full training, it becomes impossible for most labs and the companies because especially in nano or things, right? Nano specific things or bio specific things. It's the data set is very huge. It's a million or trillion. So those type of companies are the LLM sizes, right? It's exploded. So the organization needs the cheap and fast modular ways to introduce the new skills. So the early researchers, right? Also, they initially first they discovered with adding a small layers or like prefix vectors that could steer the model. So instead of changing all the fine tuning all the parameters of the model, the base LLM, you are freezing most of the parameters and taking only the adaptation layer and changing only that adaptation layer based on the requirement. So the adaptation allows the new capabilities without touching the original billions of bytes. So that what that billions of bytes, right? That will be freezed. So only your adaptation layer only it will take into like for playing that whatever your fine-tuned your LLM, right? It works. So this is the innovation slowly laid the foundation. This is a foundation for parameter efficient fine-tuning. So what is model adaptation? Model adaptation, right, refers to the already said techniques that modify or steal the pre-trained LLM without changing the original matrix. Instead of training the billions of parameters, adaptation adds a small specified modules, example adapters, prompts, prefix vectors. So the goal is right to teach the pre-trained model new patterns or behaviors cheaply, safely, and modularly. So adaptation allows a model to adjust its output distribution for new tasks while retaining the general knowledge acquired during the large scale pre-training. So the adaptation techniques are lightweight, reversible, stackable, and making them ideal for rapid experimentation. So adaptation, why adaptation before fine tuning becomes popular? Because the early LLM were too large and expensive to be fine tuned because of the LLM size and required specialized hardware and unavailable to most organizations, and full fine tuning caused the catastrophic, especially where we go for parameter reduced fine tuning, right? So that as well as the your adaptation, right? When the full fine tuning fails, the catastrophic forgetting that may arise when you are handling with a huge data set. So where the model lost previously learned the general knowledge. So the adaptation methods allows the researchers to introduce a task specific expertise without rewriting the core model. So the adaptation addresses the need for efficient customization when datasets were small and computational budgets were low. It provides a flexible mechanism to plug in new capabilities without de-establishing the predefined models foundations. So this is what the model adaptation. If you see that the existing pre-trained LLM models, right? It's mostly it's frozen, so tiny adapters. So afterwards, you are introducing the adaptation layer. So this tiny module steals the output of the new task and leaves the core model is frozen. So they are not changing or anything playing with the those parameters because billions of parameters. So no catastrophic forgetting is going to happen over there. So they inserted the small layers and transform the hidden states, add the vectors and guide the attention patterns, and finally auxiliary networks influence the output. So finally auxiliary networks influence outputs. Afterwards, these adapter modules, right, that has the especially right this adaptation layer and this adaptation models, right, that usually has the domain knowledge, behavioral rules, and stylized responses. So since these are with this help of the adaptation models, the adapted large language model, right, that came into picture. So this is what the adaptation. So this is a simple comparison between your fine tuning and adaptation. Okay, parameter PERT model also we can call it as adapted adaptation method. So here this loss and gradients are applied to all the parameters, but here right both models are frozen. But here the parameters updation, right, it's happening for all. But here the adaptive layer, right, it will tiny adapted train and adapts modifies the behavior, and finally fully updated large language model. Here adapted large language models we are getting it. So this is a simple comparison. And finally we are comparing the prompting, RAG, adaptation, and fine tuning. So it gives the prompting, we already discussed, it gives the external instructions only, needs longer input, cannot enforce a consistent behavior. RAG, right? It has the external knowledge, not the behavior, can only fetch the information, intensive to model errors. So adaptation, right, injects a task, what is not knowledge, shallow behavior change, and requires a moderate computer. But fine tuning, right, detects a model, injects a domain knowledge, consistent and controllable output, but catastrophic forgetting is the main drawback of the fine tuning. Why shift from adaptation to fine tuning? So this is what the where we are moving from adaptation to fine tuning. Adaptation methods are limited and less stable for domain critical and high stakes tasks. So again, right, since we are playing only with the limited parameters or adaptation layers, right? So sometimes you have to compromise with the efficiency, right? So when you need especially domain critical or high stakes task, then you have to only stick with the fine-tuning model. How fine-tuning works at implementation level? Here, right, it's a pre-trained LLM that prefers the task-specific data and reprocess the data, finally adjust the layer, configure the model, then train the model, evaluate the performance, and iteration and deployment. So this is the flow of fine-tuning works at implementation. But actually, right, what we said is base LLM that has a data set pre-training. Afterwards, the domain-specific data set is also given. So finally, you are getting the fine-tuned LLM we have. So whatever query you are asking. So since it gets the domain-specific data from along with the base LLM, so it will be able to give a response at a very high level, accuracy level. So this is the difference between the pre-training and fine-tuning. So pre-training, right? The pre-training is simply whatever the base model. So we have to train with the various prompt, right? So similarly, that's what the pre-training. And fine-tuning, right? Again, you are adding the domain-specific data. That's one pre-training plus domain-specific is we can call it as a fine-tuning. So here the training time, right? For pre-training, you need weeks. The time duration requires, right? It about a week, and fine-tuning about hours. And computation is it requires thousands of GPUs, but one or few GPUs more than sufficient. And data set sets are like it's terabytes, and here 100 to 1000 megabytes. And budget is you need millions, but here hundreds of dollars is more than sufficient. So, with respect to the implementation specific, it's simply we can call it as a supervised learning and unsupervised learning. So, pre-training is unsupervised learning, and fine-tuning is we can call it as a supervised. The previous pre-training, right? That is unsupervised learning, and fine-tuning is supervised learning. So, because you are getting the domain-specific data set, so here it will from the terabytes of input data, it has to like get learn and get the data, and finally it has to give the answer. But here you are giving fine tuning, then it will be able to like give appropriate right answer. So this is a pre-trained model versus the fine-tuned model. The pre-trained model, right, no data to get started and smaller upfront cost, no technical training knowledge is required, and connect data through use RAG also. More generic data fits and hallucination, but it has a hallucination. RAG misses or gets incorrect data. In the fine-tuned model, right, domain-specific data is required, involves upfront compute cost, needs technical expertise, use RAG to more high quality domain specific data and learn new information, able to correct the incorrect information. So this is a comparison. And training model to base training model, the pre-trained model, right, to learn how it text generation. That you people, many of you knows that how it is being learning. So training LLMs, right, from the scratches we can call it as a pre-training. So I am, and then I am here data scientist. So this is the way, once you type I, then it will learn am, and then once am, then if you are, so every time it will pre-training, right? So once you trained, then only it will be able to like label this kind of like a data set. Otherwise, limitations, because the context understanding, right, it's difficult. If you are a data scientist, if you are asking many that queries and all with respect to data science, then it would be able to like learn that you are a data scientist, and it would be able to like use that. Otherwise, it won't be able to. So the contextual understanding, and sometimes generating misinformation, lack of creativity, and hallucination. These are all the limitations of pre-trained model. When we need a fine-tuned model, so use a fine-tune when repeated task requires a consistent behavior, output must follow the strict format and constraint, and domain-specific strict format constraint, domain-specific terminology is required, safety-sensitive task, and RAG alone cannot enforce a reasoning or tone. So these are the various libraries used for fine-tuning, and library named DeepSeed used by the company Microsoft. PERFT, it's Hugging Face, and Accelerate, Hugging Face company, and the EMO, NVIDIA, and T5X is by the Google, and PaxML is by the Google. And this is the popularity level, and this is the one. So Here, this is the 7 stages of fine-tuning the pipeline for LLM. So yesterday we discussed about the LLM, so pipelines. So today we are mainly concentrating on the fine-tuning stage 4. So types of fine tuning. So now up to till now, like what we understood is the classical deep learning models and the evolution of transformers, and then pre-trained model, and then what are the various way to like improve that performance using prompt engineering, RAG, fine tuning, and RLHF and all we have discussed. Now we are exactly focusing on the fine tuning. Fine tuning we can classify it into like a two types. One is a partial one, another one is a full fine tuning. In the full fine tuning, right, all the parameters of the pre-trained models are updated. So this is the resource intensive, but can yield the best performance. So some of the full fine tuning models, right? Transfer learning and supervised fine tuning and instruction tuning, and then few short fine tuning, domain specific fine tuning, task specific fine tuning, and language adaptation fine tuning, and multitask fine tuning. So these are the various right. So here these fine tunings, right? For example, supervised means the instruction fine tuning and the right, the instruction will be given. So similarly, so with respect to only what aspect you are looking for, that's the one. But the full fine tuning model, right? It will requires the parameters of the pre-trained models, right? All the model parameters will be updated. In partial fine tuning, right, the PFT, right, only a small subset of parameters being updated, or new layers are being added and trained. This is much more resource efficient, faster, reducing the risk of catastrophic forgetting, and common methods include the LoRa, low range adaptation, quantized low range adaptation, prefix tuning, etc. So this is a partial fine tuning and full fine tuning are the two basic classification, and these are all the various fine tuning methods. In full fine tuning, right, already we discussed almost about so full fine tuning involves updating all the parameters and key features, right? Complete adaptation, every layer of LLM is fine tuned, allowing the deep integration of task specific knowledge and high resource requirements and better performance for complex tasks. But the limitations, right, the computational cost and potential overfitting and suitable for specialized task requiring deep integration of domain specific knowledge, ideal when computational resources are abundant and the task is complex. So now we are seeing what are the different types of fine tuning, that full fine tuning. So the entire LLM paradigm is built on the transfer learning. It is efficient because you don't train from scratch. So here, this is what the use case what we are considering. The source task, right? Predicting the next word in a massive internet corpus pre-training. This teach the LLM grammar, semantics, and old knowledge. But the target task, right? Answering the medical question. If you are asking any questions related to the medical related things, you have to answer properly. So here is the process, right? You take an LLM pre-trained on the general text transferring the general language ability, and then fine-tune it with supervised fine-tuning on a data set of the medical questions and answers. So if you have a quite large amount of data set on medical questions, then it will fine-tune that. So that's the transfer of learning. So that's what we can call it as the transfer of learning. And next is supervised fine-tuning. Even in classical method also we know that supervised and unsupervised reinforcement learning. You would be able to know that. So the basic that concept is being playing over here on full fine-tuning. So this is the most common and fundamental type of fine-tuning. It involves training the pre-trained LLM labeled data set. And example task is right sentiment analysis. Here the data is right, a data set for customer reviews each enabled as positive, negative, or neutral. Here the process, right, you fed the LLM review text like the service was excellent. The train it into the output is positive. If you also feed this product is broke weekly, then train into that it is negative. So this is the way you have to supervised method, right? You have to train it, and finally you will get the result. The fine-tuned LLM becomes highly accurate at classifying the sentiment of new, unseen, and reviews. Few shot fine tuning. So this is a few shot. So this refers to the ability of the large pre-trained LLM to learn new tasks or adapt to the specific style with a very few examples provided directly into the prompt without any actual weight updates to the model. So here the extracting the product names from the customer feedback. So here the customer has given the feedback. So once they given the feedback, we have to just only the extracting the product name. So in the feedback, if they have given the product, the company name, then you have to remove that one. I think the first one, the review was, I think, not that. Okay. In the second one, the customer service for the Supervac was terrible. So here the product is Supervac. The next review, right? My RoboMop is fantastic, but the battery life is short. So here the product is RoboMop. So this is the way we need to few short from the given, right? You have to. Next is the domain specific fine tuning. So pretty straightforward. We can say domain specific means what domain you are looking for, medical, healthcare, or sentiment, or whatever you like based on that, right? So this focuses on adapting the LLM to a particular industry, field, or area of knowledge, or training it on a particular specific things. The goal is to make the model more knowledgeable of the domain terminology. So here the example, right, task, right, building an LLM that can actually discuss complex financial derivatives and data is right, millions of financial reports analyzed called transcripts, economic journals, and financial news articles. This data is largely unstructured data. So here the process, right, you take the base LLM and continue to pre-train it on a massive financial text corpus. So you are giving the massive financial text corpus of financial data. The model, right, it learns a specific jargon, yield curve, quantitative easing, and futures contracts. So these are all the typical sentences and structures and factual relationship within the financial world. After that, this will learn. You might perform the supervised fine tuning, right, or domain specific fine tuning for a specific financial task like sentiment analysis of earning call transfer, give you the right appropriate answers. Next is the parameter efficient fine tuning. So whatever we discussed the previous model say, those are like a, almost they consider all the parameters, but here we are consider only the limited parameters. So here parameter efficient fine tuning, right? This focus on modifying only a small subset of LLM parameters such as attention layers or embedding while keeping the majority of the model unchanged and techniques like low rank adaptation and adaptation layers of predict are commonly used. Here the key features, right? Resource efficiency and faster training and preservation of the general knowledge. But the limitations, right? Since we are only using the adaptation layer, since it's only subset of parameters updated, but may not achieve the same level of specializations as like a full tuning. So task specific constraints, right? The PEFT is best suited for a task that do not require the extensive reconfiguration of the model. So it is recommended for the resource constrained environments or for fine tuning as extremely large models, best for tasks that requires a slight adaptation without modifying the core structure of the LLM. So this is what see if you see that, right. So this is what the LLM and when the fine tuning, right, the temporary memory, forward activation function, gradients, and optimizer states, everything, all the weights have to be modified. The QA fine tuning and summarizing the fine tuning, generative fine tuning, all the parameters have to be updated. So the data is right like GBs in terms of GBs. And when you go into the partial right, fine tune right says like space and as well as flexible because whatever QF and summarize partial right, decentral right, it requires only MBs because only you are changing the adaptation layer, only you are changing that things. So why parameter efficient fine tuning, right? One of the major challenges with fine tuning LLM is their size. If you see that it's in terms of GBs, but here in terms of MBs. So fine tuning retrains all the parameters in the model. So for example, 7 billion model, this represents the billions of weight need to be updated literally. And for 70 billion and larger models, then you have to go with the quite so much amount of it takes because the processing GPU memory is also huge, and then it takes quite a lot of time to train, and a lot of difficulty complex is there for training the model. Just for model optimizers as well as risk overfitting or catastrophic forgetting of the model's pre-trained capability. So next is that's what we moved into the parameter efficient fine tuning, a set of techniques that instead only tune a small portion of model parameters, drastically reducing the resource requirements with the PERT instead of modifying the 100% of the weights in the model. So you add some small adapters weights or rack the decomposition matrix and only train those while leaving the original model weights mostly frozen. So if you see that, I think in the next, I think trade-off are given, and this is the, yeah. Here, right, most of the things are right frozen. Only, yeah, this is a model weight, and only this adaptation layer A and B. This is the one like we are changing that. So that's what mostly frozen. This research with smaller number of parameters needs to be updated. About like less than a percentage, 1%. So lower memory usage and ability to fine tune very large models on a single GPU. So obviously the trade-off will be there using the partial as well as comparing the when we compare with the fine tuning. When we go with like a partial, right, memory efficiency is there, training speed is there, parameter efficiency is also there, but the drawbacks are model performance and inference cost, right? We need to compromise on these two things. So here, what is low rank LoRa? Exactly nowadays, what we are using when we have a limited memory on our system, because right, some of the implementation when you go into the field, you cannot always use the like a high-end system. So you have to implement the LLM in a low-end system, then you have to go with the LoRa. So LLM, right, we have the model weights, Llama 70 billion has 70 billion numbers, and instead of changing all the 70 billion numbers, we instead add a thin matrices A and B to each weight and optimize only this adaptation layers A and B. This means only optimize 1% of the weights. So LoRa reduces the trainable parameters by a factor, large factor. For example, dense layer with the 590K parameters can be tuned, fine-tuned with the 7K total LoRa parameters. So additionally, less than a percentage. So additionally, since only A and B have the gradients, memory used for gradients and optimizations are small, and the original weights never change. And the original model of the LoRa is 60-bit quantized. So this is what where we are again from the LoRa, the Q LoRa, quantized LoRa is entering into the picture. So again, in the quantized LoRa, right, we are doing the quantization. So because whatever when we are using the fractions, right, especially instead of that integer, right, when we go for floating, that floating point, right, we need to quantize into 4 bits instead of 16-bit or 32-bit. The Flora, Q LoRa, right, quantize the values into 4-bit floating point, and that saves the 73% of the memory. So Q LoRa further it reduces the memory and all those computations. So this is what the LoRa. So here this is a normal transformer architecture, the base LLM. Here this one is this is a frozen weights, but we are adding A and B. This is the adaptation layer, and matrix multiply low rank matrices A and B, and then you need to add the original weight to the frozen weight. So this is the updated weight. This is the updated one. This is updated weight. This is what the vector embedding, and this is the encoder. So freeze most of the original LLM weights, inject the two-rank decomposition matrix, and train the weights of the small matrices. So this is the way LoRa will work. And Q LoRa, right? Q LoRa is a related approach that quantizes the base model weights into 4-bit precision during the training. Normally, fine-tune a large model, you would load it with 16-bit or 32-bit floating precision, which requires a huge amount of memory. Q LoRa loads the model using only 4-bit integer values and then applies to the LoRa on the top of it. This can reduce further memory usage by the order of magnitude. So introduces a 4-bit normal float point and data type for 4-bit quantization. So unified GPU, CPU memory management reduces the GPU memory usage, and LoRa adapters at every layer, not just attention layers, minimizes the accuracy and trade-off. And this is finally we are coming to the final thing: full fine-tuning versus partial. Full fine-tuning, right? The optimizers are like this one no adapters. So you are changing all everything how the LoRa and as well as the full fine-tuning rate that use a base model. But the Q LoRa rate, it won't take the base model, it quantized model it will take, and then no, without adapters, all parameters are getting changed in the full fine tuning. But here only the adaptation layer alone getting changed in the LoRa. Here in the format that is a base model, quantized base model, adapters are being changed, and finally you are getting the response. So this is the way finally the fine tuning and partial fine tuning LoRa, Q LoRas are like playing vital role, and based depends upon your application and depends upon your system memory constraint and everything, right? You need to select what type of fine tuning is required, full fine tuning or partial fine tuning. But this is highly mandatory to get the efficient response without any hallucination. So this is what, that's what I'm saying. This is the heart of the implementation of your application, sir. So that's all about today's my theory part. So whatever how this like fine tuning, right? How it works with respect to real time in background. That is in backend how it works and all right. That my student going to like show a small demo. I think Santosh, are you in online?
Yes, I'm here.
Yeah. Please show the demo, but don't take much time because I took much time.
Yes, sir.
Yeah, please. Thank
So,
you.
sir. Good evening, sir. And this is Santosh, and
Yeah.
I like to present today's practical session of fine tuning. So, actually, we have many types of fine tuning, and Perumal Raja sir told about Q LoRa and LoRa fine tuning. So, here I have some practical implementation of fine tuning. I'll just present my. Okay. Okay, so in fine tuning, actually, my sir told we can actually fine tune a model to give a exact format. So in LLM pipeline, we actually use LLM to extract any information or to analyze any information. We want the output in a very exact format. So actually, in a normal LLM, if I go to any chat GPT or any LLM, if I give any clumsy data like this, extract the product information, where I have some HTML code here. So div, there is a product class and I have an exact product here. And there is a price class and I have the exact price and the category and brand. So it is in a very clumsy manner, arranged in a clumsy manner inside a HTML text. So if I give this data to a very normal GPT or LLM, like this is what it gives to me. Like it actually takes the product what I want, but the format will always change when I execute it. So every time when I give the LLM a task to extract these products, these datas, it will actually generate a text to in a way that a human can understand. But in a pipeline where we use a LLM, we don't need always a different format. So we may need something like this. We may need something like a JSON format where always the keys will be remaining in same way like how we want. So in a non-fine-tuned model, it may vary always. We have name on time, a product name on time, and a product name again, but without this this minus mark here. So like every time when I ask for a response from an unfine-tuned model, it will generate a random kind of format. And when I fine-tune a model to generate in a specific format, I will get a very specific output like this. So let me go through the data set I have. So what I did is I just made a data set like where like I have this input text where like extract the product information, same as what I showed you here. I have this clumsy data here, and yeah, output what I expect. So it is basically like a question bank how we used to give to students. So like we give a question and an answer. So similarly, I have 500 samples here. So it will have a question like what kind of input I will give and what kind of output I expect. So every answer here has a same kind of format. So my fine-tuned LLM will understand there is some pattern behind that every solution. So it will know how to answer for every question I ask. So I will just show you. I have actually implement like I will go through this notebook here. Like I will also share this notebook. It is actually a framework called as Unsloth. Yeah, Unsloth is a framework we use to fine tune LLM using LoRa. Yeah, it is a part of open source community from Hugging Face. So Sar would have told that we there is something called as PEFT. So it is a method we fine tune a LLM from Hugging Face. It is proposed from Hugging Face. So they use the same concept here. So Onslaught is also a open source community along with Hugging Face. So what I just did here is like I downloaded an open source model called as Pi 3. It is a model from Microsoft. So I just downloaded it in a 4-bit model. So it can run on my VRAM. Actually, I have only 15 GB of VRAM, I guess. I have only 15 GB. So such a resource constraint. So usually like we used to fine tune LLM in more than 100 GB. So we can't afford 100 GB right now. So like we are using our 15 GB of VRAM using 4-bit LLMs. So I just downloaded the LLM here and loaded them to my GPU. So like just I'm going to test this LLM before fine tuning. So what I did is I just gave this whole prompt to this base LLM. This is my base LLM. Extract the product information, and these are the things like my input. So what we expect is the output, which is formatted by its own. So we can see here there is a clumsy input, and assistant have replied the product information extracted from the provided HTML as follows. So can you see like so every time when I execute this model, I will get a different format here, which is not required in a industrial standard. When I go to an industrial standards, it there is a some format to be followed every time so that the next step after this can be executed without any problem. So what I did is I just made the data set to be loaded here and prepare the LoRa. So actually LoRa is a low rank adaptation method where I used to fine tune only few parameters in the whole LLM part. So if we see here, like we have the whole model weight here, like we just saw PPT. Perumal Raja sir just showed us. So this is the model weight. We will freeze this. We will make our own matrix, a duplicate matrix, a fresh matrix near to the model weight, and train those matrix. So I will just do them here, and I will put the parameters like how many epochs I should train, what should be my learning parameter, what should my optimizers. So after all defining all these things, I'm just going to train the model. So the training model will be always similar to everything. Like we have epochs and training losses. So you can see here I made 3 epochs, and at the end of the 3 epochs, I have like really low loss. So this is the time to check our fine-tuned model. So here we have the same prompt, extract the product information from this clumsy HTML data. So same, I have given the same thing. This time the model have responded something like this, where my response has the JSON format which I expect. So if I run this how many ever times, I will get the same format output. So which is something required for an industrial requirement. So like I have just made the whole notebook, and I have also another like example to show you. So something like this where okay, like we have some text, sudden, severe, abnormal pain and dizziness. There is some like I'm going to give some kind of text and it should say me what is the alarm. It should be a panic or okay or alarming. So we have three signals here. So sorry for the background noise. So the model should output what kind of seriousness is the input text. So I have just trained it. Like while Perumal Radha sir was presenting, I just trained them. So before training the model, if I give the same input, muscle soreness after exercise and dizziness, if I if I give this input to the fine-tuned model, a fine-tuned model which is being fine-tuned on something else, so it would have forgot about its previous trained data. It would have forgot how to give a formatted output, how it was giving before. So if you see here, if I give this input, it has given me something like this, which is not at all an answer. So it is something hallucination, complete hallucination. So what I did is I just did the same like LoRa setting up and my data set preparation and setting up my parameters here. And then I have fine tuned here. Okay, like again, I'm going to test this with some other data. So from this body alarm data set, which I just showed you, this kind of thing. Let's see what kind of format it is going to give us. So like our expected output is like it should what kind of alarming thing it should say. Okay. Okay, it has hallucinated a lot. So like I should fine tune this model from back again. So in the presentation, Sir would have told about catastrophic forgetting. So the model has forgot about the base model weights. So when I fine tune these parameters, it has forgot about this model weights and it started hallucinating. If I started over this notebook again and fine tuned only on this data, only on this alarming data, it will give the right output instead of talking about the e-commerce thing. So you can see here it has started talking about something like this. We don't need these kind of things. So if we fine tune a model again and again, it is going to go for a catastrophic forgetting. And when we fine tune it for first time, we get a really good output. So we have something like this. So like this is before fine tuning and this is after fine tuning. So I guess like I made a good explanation.
Yeah, thank you so much, Santosh.
Thank you, sir.
Thank you so much. So that's all about today's session. And thank you so much to all of you for patient listening. Right? So thanks again.
Thank you so much, sir. Thank you so much, Santosh.
Thank you.
Dear participants, yes. Dear participants, if you have any doubt, please ask to us. Dear participants, you can ask in your chat also.
If you are asking anything related with implementation specific, Santosh will be the right person for because he has done so many things on implementation part we used to discuss. So maybe theory part only I'm good, but the implementation I don't have a time, and he is the one done well, my pet student.
Dear
Even
participants, don't hesitate
offline
to
also, you
ask
can feel free to
your
discuss with
doubt.
me and get our help.
Dear participants, if you have any doubt, or else we will wind up the session. Hachuri sir, shall we wind up, sir?
Yes, ma'am. If you know queries means, please wind up.
Okay.
Thank you very much, sir.
Thank you, sir. Thank you so much for giving that opportunity. Thank you, ma'am.
Thank you, sir. Thank you, sir.
Thank you so much, sir.
No
Thank,
queries, please
thank you, ma'am.
drop the
Thank you
chat.
so much. Yeah, thank you.
Okay. Dear participants, kindly fill up your feedback and quiz today night 10 p.m. before. Thank you. Thank you to one and all. We will meet on next session. Thank you.